Well, it's a great pleasure to be in Chennai. As many of you know, that I'm coming quite often and always with the greatest pleasure here. I would like to thank IMSC for invitation, and more especially Professor Sayantan Sharma for kind invitation. Well, about what I'm going to say. So we are here in community with physicists, computer scientists, mathematicians, and from different sub areas, and so I try to do something which hopefully is understandable, and please do not hesitate to interrupt me if there is something you want me to make clearer. It will be with pleasure. I would do that. So I want to speak about a few things we can prove about some of cubes, but it's to illustrate more what we can do with that, because there are things we can prove. Don't worry, I won't give the proofs. There are things we cannot prove, which is also very interesting, and also then what can we do if we can't prove? Well, what can you do to be more or less convinced that everything is working? My regretted colleague Alf van der Poorten, Australian famous mathematician, used to say there are two kinds of theorems. There are theorems you have here, and there are theorems you have here. And I want to talk also about theorems we have here. Of course, the game is to transfer a theorem you have here into a theorem you have here, but this doesn't work always, and you have to manage with that. So, okay, cubes, the actors and the plot. The actors, cubes, you know what they are, so it is rather quickly increasing sequence. And Waring stated something which is given in English below, that every integer is the sum of at most 9 cubes. And so the reason there's something why the 9 is coming from, this is about clear. 9 is coming from the fact that there are numbers that require at least 9 cubes. You see, if you take 23, it is less than 27, so you can use only powers of 2 and powers of 1, cubes of 2, cubes of 1. And you take as many, of course, cubes of 2 as you can. This is 8 plus 8. You cannot take a further one, because otherwise it would be 24. And then you complete with 1, and you need 7 ones. And this is why you need 9 cubes. Of course, Waring was stating, but there was clearly no proof. He was computing, I don't know up to what he was computing, maybe a few hundreds. But well, if you try to do it by hand, you notice that you cannot go very far. And by the way, even with machine, it's not that easy to get good algorithm for treating this problem. This will take later on. So what are the first results? Edmond Maillet in 1895 showed that at least there is a finite number of cubes. It was well known, for example, for squares. It was known from 1770 by Lagrange. For fourth powers, or biquadrates, it was known that it was possible to represent as the sum of a finite number of biquadrates already by Liouville in 1859. Cubes were more difficult because essentially all those elementary proofs rely on polynomial identities. But if you have a biquadrate, you are sure it is positive, or a square, you are sure it is positive. For cubes, the difficulty is that you have nice expressions, but you have to check whether the elements you are producing are positive, and this is a difficulty, and a difficulty even later. So Wiefrich and Kempner, 1909 and 1912, proved that Waring was right, that is to say 9 cubes is okay for representing all the integers. So there's one point here, why to put two names and two different dates. Of course, a theorem can be proved at different periods, because someone is proving it, and then someone comes later and gives a much simpler proof. I mean, some people came later and give a more complicated proof, but this we don't speak about, and give a simpler proof. No, this is the same proof, and indeed there is in Wiefrich something that a little gap in his proof. And Kempner noticed that and filled the gap, but definitely the method is exactly the method of Wieprich, and so it would not be fair in some way to give the name just for the last one, with just taking everything, and Wieprich really is to be credited for this. Indeed, the same year, not only the same year, but in the same journal, Mathematicians Allen, one after the other, Wieprich and then Landau published that every sufficiently large integer is a sum of at most 8 cubes. So that is to say there exists some bound above which elements are sum of 8 cubes. One interesting point, I am going to say that maybe for Linux we'll see that. But okay, his proof is in some way effective. That is to say, he could give a value. You can deduce a value for his proof, and then you just to fill the gap. But if the gap is too large by numerical computation, and you don't know that, okay, you don't know it. In any case, it's fine from some point onward. Every integer is a sum of 23. And Leonard Dixon in 1939 filled the gap and proved that indeed there are only two integers which cannot be represented as sum of 8 cubes. One is 23, we already gave the proof of that. The other one is 239. And then beside those two numbers, every number can be written as a sum of at most 8 cubes. And Linux in 1941 showed that every sufficiently large integer is the sum of at most 7 cubes. Situation for 6 cubes is that nothing was known, and still now nothing is known. A very difficult problem. Is it true? Everybody would believe that from some point onward every integer is the sum of 6 cubes, but we don't know anything about that. So let us go to smaller values. What was known at that time. Davenport in 1949 showed that I used the symbol C4 and C3. C4 will denote a number which is the sum of at most 4 cubes. Okay, C for cubes and 4 for the number of representation. Then C3 means the number of elements which are sum of 3 cubes. So Davenport proved that almost all integers, that is to say you count all the integers up to x, what you have is something which is almost all, in the sense that the frequency you have, if you divide this number by x, what you get is something which is tending to 1 as x is tending to infinity. And Davenport, the same Davenport, 1 year later, Harold Davenport, got a lower bound for the number of n up to x, which are a sum of 3 cubes. It is a slight power of x. We see what we would expect for sum of 3 cubes. Okay? And there were a few numerical computations. You see at that time, you had to do it more or less with your bare hands, and you couldn't go very far, and you understand why definitely you need computers to do something for knowing what is the behavior for sum of 3 cubes, for example. Okay, so what to do? We consider the number of representations, not only whether an integer is representable or not, and we'll see that this is a quite interesting approach. By the way, the approach of looking at the number of representation in an additive problem is something that comes back to Hardy, Littlewood, and Ramanujan. Ramanujan and Hardy were studying partition, as you know. Ramanujan was studying partition, but to know what is the number of partition of n, with Hardy they found a method which is known as the circle method, which permits to give some asymptotic for the number of partition of an integer n. And Hardy and Littlewood developed this circle method for the case of sum of powers. This is, by the way, what we used with Ballou in what you referred to a few years ago. Okay, so we are looking at the number of representations, number of ways to write n as a sum of 3 cubes. Now there are several representations. You may accept that they may be equal you may accept that you take them in different orders, you accept that they are not in increasing order. In any case, all those representation functions are very close one to the other. You see, if you accept that two are equal, essentially it means that you are using one cube less, and then you have something which is much smaller. So there is some error term. So definitely do not pay too much attention to that. Any number of representation you like is good. With the order, without the order, with equality or without equality, this is fine. Now, if you look at this number of representation, then of course all the cubes we have here, if you write n, all the cubes are at most equal to n, because you have a sum of positive elements. Each element is less than the sum. Okay? So now if you look at all the possible representation, when you sum them, you are just counting the number of s-tuples of elements which are less than n to the 1 cube, or if you go up to x, which are less than x to 1 cube. That is to say that this upper bound is somewhat trivial. Summation of Rs of n is at most x to the s over 3. Just because you count the number of s-tuples of elements which are at most x to 1/3. Okay? And even you can win a tiny bit by using the fact that if you take all the tuples, but then if you had to put them in the good order, since they are all different, this is where it plays a little role, then you have s factorial possibility of representing them, and so you have this. Now you can indeed work a bit more, and more precisely you can show some equivalent for this number. It is really of the order x to s over 3 times some gamma factor. Essentially you will have some, you see, a Dirichlet integral to compute, because if you take all of them, you see, if you take all of them up to x, you also represent numbers which are larger than x. If you take all of them here, which are something like x over cube, then the sum is larger than x. So you have much more than what is needed. If you take exactly what is needed, you have this. This is the value of gamma s, and what is of interest for us is gamma 3, and gamma 3 is something like 0.11 and so on. This is well known. There's nothing difficult in that representation. So this is already interesting. Maybe I put that, yeah, okay. So our 3 of n, 3 divided by 3 is equal to 1, and you are counting the number of summing the number of representation up to x. So it means that R 3 of n is constant on average. Not only constant, but the constant is small. So you are sure that you cannot represent all elements as sum of 3 cubes. If you are lucky, you have a positive density in the way that up to x you have something which is a constant time x. This is the best you can hope. And on the other hand, R4 of n tends to infinity on average, and then you would expect, okay, if the number of representation is tending to infinity, then possibly all the elements are representable, or at least all elements from some point onward are representable as sum of 4 cubes. Well, you may expect that. By the way, it may be not easy. For example, this is not solved at all. We don't know about the fact that every integer sufficiently large is the sum of 4 cubes. We don't know it even for sum of 6 still now. Those problems can be very difficult. I quote another problem in additive number theory. Take sum of 2 primes. We expect that every even number is a sum of 2 primes. This is the strong form of Goldbach problem, binary Goldbach problem, and we are very far from knowing it. Is that expected? Yes? Excuse me. Here?
What I'm asking is, you are asking that
yes.
1 is less than n1, less than ns. So my question is,
The first one, they don't play, but definitely here, I don't want to exclude one. I don't want to exclude one. You can also put a 0, and if you put a 0 and you ask them, it will tell you that it is at most the number of elements, and whatever you define here, whether you allow 0, whether you allow equality everywhere, you have the same equivalent. Okay? This equivalent does not at all depend on what you are doing. But you are right on the slide that definitely should be equal. Okay. And even 0, if you want to say it is at most. Because if you add a 0 cube, then you may not count it. Okay. So, yeah. Okay, so now we don't know exactly what is going on, so we try to find a model to mimic the behavior of that, and it will be easier in a model to mimic indeed the number of representation and tell you this is what I want to explain. So now we have to understand what is the probability model for cubes, for example. So maybe I don't write on the board, but I use my hands. So you have some sort of almighty creature who can handle dice and takes a family of dice which are numbered, dice or coins if you prefer coins, even more almighty. A lot of coins, and on which coin there is a number, 1, 2, 3, 4, and so on, so you recognize it, and on both sides of the coin there is a 0 and a 1. So now what this almighty guy is doing is taking a set of coins indexed by all the integers, not one, and you throw them. And then what you find is that if you look at the coins, so you have a coins number 1, a coins number 2, so this is the number of coins. The number of the coin, 1, 2, 3, 4, and you look at what is the result on the coin. So the result can be, I don't know, 0, 1, 1, 0, 0, and so on. This is what you obtain. You can find a truncated version which is much easier. You take 5 coins which are numbered 1 up to 5, and you throw them, and then you get a sequence like that, and you may have different sequences. So what you do here is to say, okay, if I see a 0, now this is the result, and this is what you do with it. You construct now a sequence A of integers which is associated to this. You say 0, 1 is 0, 1 is not in my sequence. There's a 1 for 2, yes, 2 is in my sequence, 3 is in my sequence, maybe 6 is in my sequence, and so on. Okay, and you do that for all the integers. So in some way what you say is that the guy with throwing the coins is giving you the indicator function or characteristic function of a set. And each time there will be another way to throw it, you'll get another sequence. Okay? So this is mathematically what was written there. This is not good. This is better. So you have a probability space.
If you have an indicated integer,
if for example 3 occurs twice, can this dice model get that?
Sorry?
If you have a less than or equal to condition like the previous question asked.
Yes.
So for example 3 can happen twice in your sequence. How does that come in this?
No. In this sequence, each number occurs exactly once.
Yes, so it is strictly less than. The sequence that you get is strictly less than.
Yeah, each integer, so you have 0 and 1, but you don't have 2 coins with the same number.
Right.
Okay?
Yes.
But for the time being, we are trying to build the cubes. We are not trying to build representation as sum of 3 cubes.
Okay.
Okay? We are just building the cubes. Then we see how build the cubes, how we can build the representation. We are not yet at the level of the representation, we are at the level of the cubes. Okay, so this is the probability, the little omega, it just corresponds to the fact that you take your thing and you throw them. Each time you throw them, you have a sequence. This sequence depends on what you have thrown. And this is the A of omega. So you have a second, yeah, okay. Was surprised, but it's fine. What is next? Okay, so what Erdős and Rényi were doing in 1960, Hungarian mathematician, possibly Erdős is known from a lot of people because he's a famous combinatorist and famous mathematician, and Rényi was a probabilist, and possibly you know also Rényi because the institute in Budapest, Mathematical Institute of the Academy of Science, has the name of Rényi. So Erdős and Rényi built a model, and they wanted to say, okay, I want the sequence which I have here, I would like this sequence to look like cubes. We are building the cubes. So of course you don't take real coins, you take coins, but you are cheating in the coins. You decide that the probability that they go on 0 or 1 is not 1/2, 1/2, but you choose the weight so that it will look like primes. Now if you look at like primes, there is maybe no point to put again the light. This will be enough. I write lighter. Okay, thank you. If you take an integer around x, and you see, okay, what is the probability that this number is a cube? You don't know what it is, but you want to say how to figure out. Well, around this, there will be one cube, which is, for example, n cube, and then there is another one, which is n plus 1 cube, and as you know, n plus 1 cube is n cube plus 3n squared plus blah, 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 and the blah, blah, blah is of smaller order. So what is the length of this? The length of this is just 3n squared. Okay? And if you want to see what it is with respect to x, x is something like n cube, and so n is x1 cube. So the number of elements you have between 2 primes around x is something which is 3x 2/3. Just the derivative. Okay? And this is why Erdős and Rényi said, okay, let us say that when I take an integer n, it will be a cube, pseudo-cube, with a probability 1/3 n to 2/3. This is exactly what they say, and what they give. And by the way, then you can prove, for example, this is the first statement in that. I mean, this is a mathematical result. You can prove that this is something you can do, and then you compute this, and what you can prove is that indeed the cardinality of the element in your sequence up to x is equivalent to x to 1/3, almost surely. So your sequence really looks like a sequence of cubes. Fine? So you have built something which is some random set, and now with random set you can do something, because maybe you can prove something which is for almost all. That is to say, the measure of the omega for which this has the good property is 1. Okay, now we enter. So okay, for the time being we have built cubes. Now we want to go to the. You remember? Maybe I write it again, that I have a random variable psi, a lot of random variable, but for each n I have a random variable psi n, and I say that I have a cube psi n of omega can be equal to 0 or 1, and if it is 0, you say it is not a pseudo cube in my sequence corresponding to the drawing omega, and if it is a 1, it is a pseudo cube. This psi n is exactly what is here. This is the value of psi n of omega. Okay? And this is n. Okay. So psi n of omega is 0 or 1. It is a 1 if you are in your sequence. Now when you want to go to the next step, you want to model, to give a model for the number of representation. It may look complicated. It turns out that it's quite nice. There is a nice formula which is easy, which is just this formula. That is to say that if you make the product psi a of omega, psi b of omega, psi c of omega, you make the product of elements which are 0 or 1. So it is 0 if one of them is 0, and it is 1 if all of them are 1. So when you are summing for all the ABC, for which the sum is equal to n, those random variables, the values, what you get is a 1 when A, B, C are in your sequence of pseudocubes. So this is really this which gives a model for the sum of elements. Okay? Well, so now this is the beginning, so I can take time. Now then we go to proving something, and then I can go quicker because this is more difficult. Now what they prove is that this sequence of 3 of n almost surely follows a Poisson law. By the way, this is what you expect. You see, when we have an average which is constant, usually you have something, if things are normal, you have something which is a Poisson law. Okay? So you expect a Poisson law means that the probability that this number is k is something which is lambda to the k divided by k factorial e to the minus lambda. This is the Poisson law with mean value lambda. And your mean value is gamma 3 of k. Okay, so this is something that you are supposed to prove, that you have this, and it's not completely trivial. I tell you even more than that. So now if you look at what is the density for sum of 3 cubes, 3 pseudocubes, put the cubes in bracket because this is almost always the number of sum of 3 elements in your sequence which mimics the cubes, the pseudocubes, is almost surely, well, you see the probability that you have no representation, this is when you have a 0, is gamma 3 to the 0 divided by 0 factorial, this is a 1, and e to the minus gamma 3 is e to the minus gamma 3. So this is those elements for which you have no representation, but those for which you have a representation is 1 minus this, so it is 1 minus gamma 3, and it is something which is about 1/9. Okay? So we have now a nice model which tells you in the probabilistic model, yes, numbers usually are the density of numbers which are sum of 3 cubes exists, is positive, and here is the value, is 0, it's about 1/9. Let us say quickly. Okay, so now the point is that it's not that easy to prove, and there was indeed a gap in the proof of Erdős and Rényi, and they considered something to be independent which was not independent, and so considered the dependence here is very difficult, even if you consider that your random variables are independent. At the beginning we put that. So this has been filled by Gogol and students of Wirsing, and later by Landau, and now there is however a weakness in the model, that of course this model they were not doing only for cubes. You can do that exactly in the same way for squares, for biquadrates, for different values. You have a model like that, and for squares it gives you also the fact that there should be a positive density for the one which are representable as sum of 2 squares, but this was known by Landau already in the beginning of the 20th century, that sums of 2 squares has a 0 asymptotic density. Well, so this was called, you don't see it here, I don't know why, but okay, this part is called prehistory. So let us summarize what we know. Sum of 9 cubes as well as sum of 8 cubes are well understood. We'll see what is for sum of 8 cubes. Sufficiently large integer sum of 7 cubes, but this result is ineffective. You cannot produce from the proof given by Linux, you cannot find out a value, even if it is 10 to the 10 to the 10 to something. You cannot find a value telling you from some point on what is true, because he was using something about distribution of primes in arithmetic progression, and you have something which is called Siegel zero, and he was using Siegel zero to locate primes in short arithmetic progression, and so his proof is ineffective. Okay? Almost all integers are sum of 4 cubes. this was not, it was everything you can compare. I think at that time, in the prehistorical time, you don't know when it's prehistory, but I will tell you soon. I think everybody was, the general belief, what I'm saying, almost all integers are sum of all cubes, density is 1, in that sense. Everybody believed that from some point on 1 is fine, and the situation for 3 cubes was not satisfactory. For example, Erdős in the late 60s, when I met him, was definitely in favor of a 0 density for sum of 3 cubes, as it is for sum of 2 squares, saying there must be some arithmetic behind which makes the density be equal to 0. Okay? So now we are going to enter the historical period, and I tell you when is the historical period is 1962, as you can imagine. This is why we're here today, for understanding that 1962 is the beginning of everything. So I give you the result not in chronological order, not all of them, because then except if you are ready to stay for 10 hours just, you see, quoting results, it's not very funny. At least for some of 8 cubes, I mentioned it, Robert Vaughan, many things about all this question of. By the way, he has a very good book on the circle method, which he wrote about at that period. Our 8 of n, we said that every integer from some point onward is the sum of 8 cubes, and even the only exception are 23 and 239. But he gave an asymptotic for the number of a representation. Essentially, it's what you expect, you see. If you sum all of them, you have something which is n to the 5, 3 plus 1, 8 over 3. And what you expect for each of them is you divide by n, and you get something which is this. What is that? Well, there is also in the representation something which depends on the fact that the numbers, the cubes, are not well distributed, so there will be something which depends on the arithmetic of n. Not going to write that. This is called the singular series, but don't forget about it. But something that may be of interest is maybe, for example, to represent that the cubes are residues modulo 7 of cubes. That is to say, you take a cube and you take the remainder in the division by 7. Residues are 0, 1, minus 1. This is easy to check. I mean, you have seven values to check. I don't do it here, but you can do it really with bare hands. So you have definitely something which is badly distributed. For some primes, it's well distributed. Everybody is a cubic residue, but some primes they are not, depending on whether it is congruent to 2 mod 3 or congruent to 1 mod 3. Now I use the congruent. Congruent mod something means the residue is. So for example, if you take the number 8, you will say 8 is congruent to 1 mod 7, which means that its residue is 1 when you divide it by 7. Just a question of vocabulary which is useful, but okay. So also something 19 with sum of 7 cubes. Cook and Macaulay, 1848, gave an effective version of Linnig's theorem. They proved that essentially every integer which is larger than exponential of 1 million is a sum of 7 cubes. Well, you just take your pocket computer and you check up to an exponential of 1 million and you are done. Well, just to figure out the number or something like that, what you can check is something which is about 10 to the 8, 10 to the 20, or with the modern computers, and even using a lot of computing time. Okay, so don't expect to do too much with that. Ramaret lowered down. I quote Ramaret because he's a fan of coming to this place, and is coming quite often here, and has worked with has different students also, collaborators. Prove that every integer larger than exponential, so it is better, but however, no way to fill the gap. But fortunately, the way has been filled now by 6x, in 2016, that every integer larger than 454 is a sum of 7 cubes, and you understand that this means that 454 is not a sum of 5, is not a sum of 7 cubes. Okay, so we have really the list of the number which are not sum of 7 cubes. Okay, now sum of 3 and 4 cubes. In the meanwhile, you see we had some expression for the sum of R3 of n. But then what would be interesting is to take higher moments of R3. And Hooley tried to find something for the second power. Of course, this has been understood much earlier that higher power are interested in all the work, you see that, but nothing much has been said. And by the way, what he has is a conjecture about this. His conjecture is that you have a exponent, you can represent, you have a integral representation of this, and it has some nice way to understand what should be the contribution of this. And with this contribution, this is the conjecture on that which makes sense. Of course, if you have something which tell you that even the square moments are on average finite, then you have a positive density. This is just a Cauchy-Schwarz. If you know that this is equivalent or is bounded by a constant time x, then immediately you have something like that by using Cauchy. Okay? So this was already something which now tried to support the fact that it should be a positive density. This is why when I was referring to Erdős, I was referring to what was his belief in the 60s, late 60s, but not after things like that. Okay, and for example, for sum of 3 cubes, Woolley was doing something a bit better. You remember it was something like 80 something instead of the 91. This is extremely difficult. For example, 10 years later, I didn't write it, in 1995, he proved the same thing with here 68 instead of 70. So it's rather hard. It's really because, I mean, the point is not to improve this value by a little thing, but there were really new ingredients. This is what is interesting, of course, then. It is the method. It's not the result in itself, but the method. Although it is much easier to talk about the result than about the methods. With François Encart and Bernard Landreau, we made some computation and found out this number, which is not a sum of 4 cubes, but which is supposed to be the last one, because we were able to go further and to show that then there were nobody there, and to have, well, some reason to believe that this is the largest one. Those computations have been done further more recently and confirm the fact that this should be the situation. But this is not a proof. This is simply computation. Okay. Now what we did also with the same guy about at that time was to look at compute C3 of x divided by x. That is to say, you compute the number of elements which are sum of 3 cubes up to something. You divide by this number and you see what you can find. And what we can find is some value which is like that. It is a bit less than what the Erdős-Renyi model would tell you. You remember it was about 1/9. We are closer to 1/10, a bit less. I keep this in mind, and my mind is here, 0.0999. I'm sorry for those who are here. They can't see everything, but okay, maybe 3 or something like that. Okay. I tell you something about this computation later on, but okay. So, okay, in the next few slides, by the way, I've reduced the slide. There is only 2 slides. In the next 2 slides, we present the probability model we developed in 1998. That is to say, before the computation. Indeed, those computations started around 2000, 2002. So you see, the problem with the Erdős-Renyi model is that it tells you that something which is congruent to 0 mod 7, for example, or which is congruent to 2 mod 7, for example, anything which is congruent to 2 mod 7 comes out here, because we are just saying, okay, I throw my dice, I don't prevent something which is congruent to 2 mod 7 to receive a 1. This can be considered as a pseudo-cube in the Herder-Schrenny model. So, but the point is that in the real life, this can never happen. This is not a cube. 3 is not a cube. 4 is not a cube. 6 may be a cube, because 6 is minus 1 for modulo 7. Okay? So there was a problem that this is a weakness in the Herder-Schrenny model. You see, there is something in number theory usually when you look at the problem which is the following. When you want to understand what is going on, essentially you have two things: whether the global number of things are going on nicely, Archimedean valuation, and also you want to see that locally, modulo something, modulo different integer, modulo primes, modulo prime powers, it behaves nicely. Okay? And if it be, at least you don't have always the reciprocal, but you have something which tell you it is not behaved nicely, then the result will not be nice. What you expect is that the reciprocal is true if it behaves nicely locally also for congruences, you are happy. For example, you have the same thing, residues mod 9 are 0, minus 1, minus 3, and so if you take a number which is congruent to 4 or 5 modulo 9, you will never represent it as a sum of 3 cubes. So we already did this, and in the Herder-Schrenny model, you take anything which is congruent to 4 mod 9, yes, it has a nice number of representation. So obviously there is something wrong with that. Okay, now we want to use this uneven distribution. So we cannot say at the same time we're giving, you see, give an integer. I'm looking at 5, at 6, 100. If you say this number has to be a prime, its residue has to be the residue of a prime for all the modulus or the moduli, then it's not very serious, because it means immediately that this number is a cube. It means that this number is a cube. If something is a cube modulo all the residues, it is a cube. So what you do is the following. You start by taking an integer k. You build a probability model for cubes which agrees with the distribution of cubes in arithmetical progression modulo k. You take k, of course, which will be rather large, and taking into account all the small primes and prime powers. Okay? How do you do that? Well, instead of considering as you, there should be a 2/3 here. Okay? That is to say that we are taking exactly the model Herder-Schrenny model, because it's good. It tells you that the number of primes is what we expect on the long run. But then we say also, if a number is well distributed, if n has many representations as a cube, then I will put the weight which is good. If a number is not representable as a cube, then I will put a weight 0. So if you take k is equal to 0, for example, you would say, okay, I put the weight 1/3 times n to the 2/3, again, sorry for the 2/3. You take something which is that, but then you put a weight 0 if it is congruent to 1, 2, 3, 4, 5 modulo 7, but then you put a weight 3 if it is congruent to 1 or minus 1, because you have many cubes which are congruent to 1 or minus 1 mod 7. So this is the way we are just modifying the Herder-Schrenny model like that. Okay, and so you build the same thing, and what you get is something very nice. We are very happy to find that. It took some time to prove this limit, but this is a theorem in some way. It's not at all a number theory theorem. It is a probability theorem. You build this model, and in this model you prove that almost surely you have a density when k is fixed, and when ks tends to infinity, eating all the primes, all the prime powers and the residues, then the limit is this one, and then you are quite happy because you see in the memory we had found something like that. So we are very close. So this seems to be a good model. In some way it comforts you that this was because we were not going far enough, but it would be that. Maybe a little anecdote. That's something else to tell, but a little anecdote is that how it went when we were doing the computation. You see, during the computation, this was done before the computation, the theoretical thing. So we know that we have our theoretical limit, which is 0.099945 blah blah blah. And then we were computing. But it takes time. It took time and still takes time. And so it went down, down, down. Okay, fine. You see, this is why when you see something like start like that, this was maybe what was possible to do in the late 60s. Is it going to tend to a limit? Is it going to tend to zero? There is no real way to say what it is. Okay? And then we went on, and we went on, and when we were about at 10 to the 12, bling, we went below the theoretical value. This is not the case for biquadrate. For biquadrate it's very nice because it stays always above. You can do, of course, exactly the same thing. So we are very happy. And then we went on, and by the way, when you reach 5, 10 to the 12, you see, it seems to go a bit upwards. And go a bit upwards, and when you are at 5, 10 to the 14, this is where we stop computation. We were not too far here. And then we try to imagine what it could be for 10 to the 18. And by computation for 10 to the 18, it goes like that. And this is the value you had with a 3, with 3, 5 instead of 4, 5. And when you see that, you may think that this model is rather a good model. So definitely, in some way, sum of 4 cubes now, they are really well here. Not yet here, but at least we have that. Okay, so now if you make a block construction, that is to say to take care of k and then to a k which is a bit larger and going like that, what we have is the probability model, which has the following property: almost surely a random sequence given by this model has the following property, that it looks like cubes in all arithmetic progression, and sum of 3 cubes have a density blah blah blah. This almost surely. So this is really a theorem. It's not a theorem in number theory, I repeat, this is a theorem in probability theory. It's not completely trivial theorem. Okay, I still have a few minutes, and I want to talk about this sequence. You know, there is this online encyclopedia of integral sequences. This is very, very interesting, this Sloan project. If you have a sequence and you don't know what it is, you type the first terms and it gives you a certain number of possibilities. Okay, so there is this sequence, and the Turkish guy, Alto Halkan, attracted our attention on that. And this was at that time. Nowadays it's even better, and definitely you see that you think that from 13 on everything is in this sequence, and the term of the sequence has been computed. I write who it is. This sequence gives the integers n, for which we know that n factorial is the sum of 3 cubes. This is why Alto contacted us, because he knew that we were interested in sum of 3 cubes. And it gives a decomposition. This is easy. It's always easy if you know a decomposition to check that it is the sum of 3 cubes. This you can even do with your bare hands and paper, a large sheet of paper, and you can do that. Now there are two things which are, so first remark is that you see, even if this is known, that you cannot do better than that for the density. One element out of 9 is not a cube. So there is something curious for n factorial that almost all n factorial are sum of 3 cubes. They don't behave randomly. Why is it so? So you want to explain it. I mean, when you see all that, you see really there is something, it's not 1 out of 10. There should be something to explain. So I want to explain that. Here I go quickly. Why is it possible, for example, to prove that 59 factorial, which is very large, is a sum of 3 cubes? We can go to a sum of 3 cubes, let us say, being optimistic, up to 10 to the 30, but this is 10 to the 80. Well, you see, this number with 25 decimal digits, you can write it as a sum of 3 cubes. And what is interesting is that 59 factorial is a cube times this number. And a cube times a sum of 3 cubes is a cube. The product of 2 cubes is a cube. Good. So you take out, if you can prove that, I go quicker. So now, I come back into the end. We built a probability model in which we have this. I just repeat what was our probability model. And now, motivated by this question of n factorial, we proved another property in our model. And this property is the following, that if you take a sequence US with S in this interval, factorial S over 2 factorial S, such that it is divisible by a rather large number, but the product of the primes up to S to square root of S, let us say, it's much less than S factorial. But, so what we are saying is that if we have a sequence which may go to infinity quicker, which is something, for example, S factorial itself. If you take S factorial itself, then in our model, almost surely, it is a sum of 3 primes. So the point is that if you have an integer which has a large cubic factor, then this integer has much more chances to be a sum of 3 cubes. Sum of 3 cubes. So this is what we saw with the n factorial, and this is what we get. There is sorry, this should be S factorial. I have to correct that. So in our model, almost surely, if n is large enough, n is a sum of 3 pseudo cubes. Good. So it was nice to see that our model, which was built for something different, was able also to explain why in our model, at least, we have the property for factorial n factorial. Okay, I let the last word to Terence Tao. The models are so effective that analytic number theory is in the curious position of being able to predict the answer to a large proportion of the open problems in the subject, whilst not possessing a clear way forward to rigorously confirm these answers. And this is something that Terence wrote for quite different problems, but this is definitely the situation in analytic number theory. We start to have rather good models. I gave you one example, but difficult, hard to prove things. Okay, thank you very much for your attention.
Thank you, Jean-Marc. So, any questions from the audience?
Wow.
Sorry?
This is a disaster. Yes. Oops.
Okay, when you mentioned Renier, I know those two names from graph theory. I mean,
yes.
Is it the same?
Yes.
No, it's the same people, but is there a connection with the model you described and random networks?
Renier was also a probabilist, had interest also in probability theory, and Erdős built probabilistic models, started to build probabilistic model in the late 30s. Possibly the first intervention of probability was due to Turan in 1934 for his proof of explaining what is the number of primes of an integer, and he was considering considering the prime factors as giving, there's a probability that a number is divisible by a prime, and so building something, it was on the multiplicative side and not on the additive side, but it was also something making a probabilistic model. And this probabilistic model led him to give a much simpler proof for counting number of prime factors than what was done before. And then they collaborated with Erdős on different points, and possibly one of the first things that Erdős did was the problem of Sidon, about a number of representations, and what he gave, that the question was, do there exist a sequence for which when you are looking at R2 of n, you want R2 of n to be not too large. So is it possible to find a sequence such that R2 of n is always positive, that is to say every integer is representable as a sum of two elements of this sequence, but n should be less than n to epsilon? This was the question. The answer by Erdős, which followed exactly this random construction, led to the fact that there exists a sequence for which this is at most log n, a power of log n, I don't know what, and this is larger than a power of log n, possibly even log n, or maybe some power here. Don't remember clearly. But you see, it's much better than having something a power of n. R of n is between 2 power of log n. Of course, this tells you that you can represent every integer because this is positive from at least from some point onward, and this tells you that the number of representation is very small. Is it possible to find R of n equivalent to something? This is a different problem, but at least he started like that. And essentially what he was saying, he was taking a sequence for which the number of representation, the probability that psi of n is equal to 1, this was something which was essentially 1 over square root of n. If you want sum of 2 to be close to 1, better to take square root of log n, and then what you do is you put something which is certain constant times log n or square root of log n or something like that, and then you make exactly the construction I was saying of the Erdős-Rényi, and then you get this result, and this was in 55. So it was before the Erdős-Rényi construction. So this has also history. Thank you for your question. Maybe something about effectivity. Very interesting to know what is to be effective or not. When you say something is effective, I would like to tell you one theorem. You know Riemann hypothesis, I think. Riemann hypothesis tells you, I better write in the center if I want everybody to see what it is. Riemann hypothesis tell you that if you take the zeta function, you have some complex function, and you want to say that all the solutions have a very specific property. So you have your zeta function, and when you take zeta plus it, what you expect is that if t is positive, you are just looking at the element for which t is positive. For t equal to 0, it's well understood where the 0. And you want to say that this equal to 0 implies that S is equal to 1/2. This is Riemann hypothesis. Okay? Now, this is a theorem. There exists T such that if Riemann hypothesis is checked up to T, then Riemann hypothesis is true. Interesting, no? You just have to check until a certain point, and then you are done. Well, now I give you the proof of this. The proof is the following. There are two possibilities. Riemann hypothesis is true or not. If Riemann hypothesis is true, you take t is equal to 1, you check up to 1 and it's okay. If Riemann hypothesis is false, then you have something which is some 0 which is wrong, and then you just have to check up to t0 plus 1 or whatever you wish. Okay? So this is an ineffective proof. I can tell you that if you have an effective proof of this theorem, your fortune is done. So effectivity is something which in some cases can be really interesting. This was, by the way, why Baker got Fields Medal, because in Diophantine approximations there were results which are not effective, and he was able to prove effective results in this direction.
I had a question.
Yeah, please.
So, when you mention about these large numbers, so I can understand this probabilistic model is very good to determine these. But if someone wants to look at like a computer program or something, then how do you deal with such high numbers and check?
No, so as it is here, the probabilistic model don't tell you much about the value. In any case, it will just give you something. It will tell you for each omega you have a limit. But then what you would try to know is what is the low of this limit and what is the mean value maybe of this limit, and should be possible, but we couldn't go really to that point. We tried to do it when we wanted to check that the number I was giving you 7 dot blah 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 is probably the largest one. We tried to look at that, but we didn't get anything satisfactory. It doesn't mean that it does not exist, but it's interesting point. What can be the low then of the largest number? You see, what you say is that, well, you know that from some point onward, so almost surely there exists n dependent of the little omega, so that from that point onward everything is true. So you take the smallest one, and this is well defined. This is a random variable, and what you're asking, what is the low of this random variable? This is a very difficult question. We look at that also with the Iosifescu, Romanian guy.
And how does people who try to check it on the computers do this? Like deal with so high numbers?
We can check something. Oh, okay. I give you another thing, which is a very interesting question of Heath-Brown. There is a conjecture by Brown, which is the following. For any n, there exists n1, n2, okay, I have to, n is non-congruent to plus or minus 4 mod 9. Otherwise you have difficulty with sum of 3 cubes. Then conjecture that there exists n1, n2, n3 in Z, such that n is n1 cubed plus n2 cubed plus n3 cubed. They are in Z, they are not positive. They are in Z. If I am lucky, yep. Maybe you heard that it was possibly 2 years ago, 2-3 years ago, that the last one that was resisting between 0 and 100, it was 42. Few years before, shortly before, there were still two resisting, 33 and 42. And 42, it's okay. They exist, and the Ni are about 10 to the 17 to the cube, 10 to the 17, sorry. And they are the shortest value. So this tells you about the difficulty. We can do things with sum of 3 cubes, and those 3 cubes are about 10 to the 13, something like that. This gives you and this was done very recently and by a sophisticated algorithm. But
Thank you.
Okay, if there is no other question, let's thank Professor Deshouillers for a wonderful talk.